All right, last but not least for this recording is force. Now I have recorded all of these previous and I clicked the wrong button and I lost everything. Um, so if this feels like if I'm going too quickly, it might be because this is about my third run through due to some technical difficulties. So if you need me to stop and explain anything, if I've missed something because at this point I've talked through it too many times, please don't hesitate to let me know. So we've talked about speed and acceleration, and now we're going to talk about force. So speed, the change in speed causes acceleration. And acceleration is the result of force. I really should do these backwards, start at the bottom. If you put a force or a push on an object, its motion will change. That change in motion, the change in motion will go from zero, maybe we're going, it's a hockey puck. You hit the hockey puck, it was at zero, now it has a speed, it has acceleration. Because it has an acceleration, its speed changes. So we can think about going up or going down. My graphic didn't let me do arrows both ways. So you can think about speed, change in speed causes an acceleration, which is the result of force, or you can get applying a force on an object requires acceleration, which causes speed. So the three pieces are very interlinked. Now we're not going to deal with speed so much, but we will deal with acceleration with force. Although in this lesson, we're not going to do any math. We're just going to kind of look at the theory. So what is force? Force is just a push or a pull on an object. We measure force in newtons after Mr. Newton. And we're going to go through Isaac Newton's 3 laws that he developed on forces. So the first law that Isaac Newton came up with, and there's some good graphics here, I'm going to explain the graphic in a second, if there's no outside force on an object, so if nothing's pushing an object that's in motion will stay in motion at a constant velocity, so it'll move at the same speed it's always had, assuming there's no friction or anything, so we kind of ignore some of those little things, at a constant velocity, and an object that's at rest will stay at rest. So let's visualize being at the rink, because ice is a nice smooth surface, there's very little friction. You hit a puck. That puck glides across the ice until it hits the boards. When it hits the boards, there's another force on it. Its motion changes. But until it hits the boards, its motion doesn't change, it continues to move. Let's take the same puck. We're going to put it at center ice. Nobody hits it. What happens? Well, it stays there. It's just not going to go anywhere because no force is on it. It stays in the same place. So an object will do whatever it was intending to do unless something pushes it to do something else. I think we could probably apply this to people sometimes. We want to do what we want to do. And sometimes there's some of us, especially, I don't think it's just a young person problem. It happens even as we get older. Sometimes we need a push from people around us to maybe get out of a rut, get out of doing what we've always done to try something new. That's like a lot like Newton's law. So in summary for Newton's law, maybe this is the easiest way to put it. If there's no outside force acting on an object, there'll be no change in motion. So let's take a look at this little cartoon. Guy's on a bike, he's traveling. He's coming towards the wall. The bike and the person are traveling together at the same speed, but the person's not tied to the bike. The bike hits the wall, so the wall pushes on the bike. It stops it. But that wall's not pushing on the person. The person is free from the bike, so the person's body wants to keep going. That's what makes motorcycles dangerous. That's why my parents were always terrified of them. The body wants to keep moving because suddenly there's no force on the body. The bike stops, but it keeps moving. That's Newton's first law. So there'll be no change in motion. The person wants to keep moving at the same speed it originally was. If you've ever been in an accident, you get that whiplash. That's because your body wants to keep going forward. And that results, you get the forward and then you get the jerk back because of your seatbelt. That is part of Newton's first law. When you're in a car and you come to a quick stop, and we've had this we don't tie our dogs in the vehicles when we drive. And we've had numerous times you come to a quick stop unintentionally, dogs are in the back of the truck, and you hear the dogs sliding in the truck. That is Newton's first law, because there's nothing tying the dogs in place, so they're going to slide ahead. They keep moving ahead while the truck stops. That's the whole reason we have seatbelts in vehicles. You've got a person in the vehicle with a seatbelt. Now, your seatbelt's not tight. Your seatbelt has room to move. Now, you can pull it out to that child lock point where it will lock in place. And I hate that feeling. But your seatbelt has some flexibility so that when you move, your body can continue to move forward. Your body keeps going forward. Now, in this case, it's not a true example of Newton's first law because that seatbelt is slowly pulling you back as you go forward to eventually stop your body. We'll find out in a second why that seatbelt slowly pulls you back instead of you stopping very quickly. We're going to think about how much force is on your body. So that's where that safety mechanism comes into place. All right, so Newton's first law, if nothing is pushing an object, it won't change motion and it won't start moving. It's either going to keep moving the way it was, or it's going to stay stopped. I think that's pretty obvious. If you're driving a car, unless you give more gas, you're going to keep moving the speed you always were. If the car is stopped, unless you give it gas, it's going to stay stopped. Okay, so there's our first law. Newton's second law. Newton's second law is what we're going to spend most of our time on with math, but we're not doing the math today. Newton's second law says if there's an overall force on an object, it will result in a change in motion, which is just what I said. If you push something, it will move. Unless friction's too big. But generally speaking, if you push something, it will move. Okay? If you push something to cause motion, it's going to start moving. If you push on a car, it may not move a lot, but it will start moving. Even if it's just that slight little roll, because it was going from a speed of 0 to even a very, very small speed, it has an acceleration. That's what Newton says. Newton says, if you put a force on something, on an object, that object has mass. Mass is like, I'm going to use, I teach a physics course too. When I teach a physics course, I don't like using mass and weight together. And I've got a couple guys confused in my other class. So please don't confuse you. But mass is like the weight of the car, how many kgs it is. It's actually how much material it makes up. But we're doing all of our work on Earth. So we'll stick with mass being like its weight, thinking of kgs. Okay. And then acceleration is how much it's sped up, how fast it slowed down. My brakes apply force to the wheels to slow them down. If I have a really large vehicle, or let's say I've just got my car loaded with a lot of heavy stuff. Like times I picked up 13 bags of cement. It's a little heavy for the vehicle. I've made the mass of my vehicle heavier, which means my brakes, I'll need to apply more force from my brakes, or I'm going to need to leave more time to stop because my acceleration, my deceleration won't be able to be quite as big. So that's what Newton's law deals with. So force we measure in newtons, I said that before, mass is kgs, and acceleration is the same as we've always done in meters per second. A couple examples. This helps us think about sizes of forces. If you have a small object like a golf ball and you put a force on it, it's going to accelerate and it'll have a large acceleration. Why? Well, it's very light. Light objects change speed easily. That makes sense. I mean, golf would be impossible if it didn't. Imagine if golf balls weighed the same amount as curling rocks. It would make the game miserable. Okay, let's say we take the same force we put on the golf ball and we put that force on a truck. The truck's not going to really go very far. It might move a teeny little bit. But why? Well, the truck is so heavy. Heavy objects resist change in motion. And that's part of Newton's law. So if an object is very heavy, it will have a small acceleration. If an object is very light, it will have a big acceleration. The other way we could think of it is if they both are going the same acceleration, if I want more acceleration out of a car, I have to give more gas or more force. The other option is, if I want more acceleration of the car and I'm racing, I make the car lighter. You do a fiberglass body. You deal with aluminum instead of steel. What you're doing there is you're changing them. You can't change the engine, so you start to change the mass. If we can make the mass very small, we can make the acceleration big, which means I can reach a higher speed. So that's how those pieces interact. Nobody ever said, let me make my car heavier so I can go slower. In vehicles, that really doesn't work very well. But it is good to think that larger vehicles, they require more heavy-duty braking systems because we still need them to slow down quickly. We need them to have a higher acceleration. So what we do is we increase the ability of the brakes to apply force. So we make it so the force can increase. Does that make sense? It's pretty logical stuff. You just probably haven't thought about it in those terms. Let's think and apply for a second. Cars are designed with safety features that allow vehicle occupants to come to a stop more slowly during a collision. How come? Well, if I come to a stop more slowly, let's see, force equals mass times acceleration. I can't change the mass. Okay, the mass stays the same on a vehicle. I mean, imagine if you go, I mean, it may be a good thing if you got in an accident and suddenly half the car fell apart to make the car lighter, or if something happened to make the car heavier, so you slowed down faster. But that just doesn't make sense. You'd have to tangle with another vehicle. It's going to be a nightmare. So we can't change the mass of the vehicle. I can't think of any way we could spontaneously make it heavier to slow it down. So we can't change the mass of the vehicle. And we want to make the force on the person as small as possible. So in order to make the force drop, if this stays the same, I need to make the acceleration go down. How do you make the acceleration go down? Well, let's look. Acceleration is the change in velocity. Well, the change in velocity is going to be the same. Acceleration is change in velocity divided by time. If I want acceleration to go down, I need to make the time go up. So what they do in cars is they make these crumple zones. So instead of the car stopping when the front bumper hits, the fraction of a second that car keeps moving while the front crumples helps reduce the force on the person. Rear crumple zone, same thing. Airbags. Airbag comes, it puts a gentle force on me, and I put on it because it wants to slow my body down so that my acceleration is less. If I have less acceleration, there's less force, less push on my body. I'm less likely to have injury. So those are some of the big things that are involved in safety. Seatbelts. As I move forward, that seatbelt pushes back on me. It slows my speed down ever so slowly, sometimes not as slowly as you might wish it did, in order to pull me back so that there's not as much force and I'm not ejected from the vehicle. So those things are designed to help make vehicles safer. I have a dog standing here by the window watching me very intently as I'm recording this. I'm not sure if he's learned anything, but if you're half as interested as he is, I'm good. Okay, Newton's third law, the very last one. His third law says that every force has an equal in size, opposite in direction reaction force. This is a great little graphic. You shoot off a gun, not that I have a whole lot of experience with guns, but if you shoot a gun, it pushes back on you. Okay, so what pushes the bullet forward pushes back on you, and you can feel it push you back. I have 5 younger siblings. My baby brother's only 20, or is he 21? I forget. So he's always roughly the age of you as my students. And yeah, if you've got siblings, you know what it's like. They push you and you push back. Okay, so that's Newton's third law, this equal and opposite reaction forces. So if you put a piece of paper on a table, if the paper's not moving, the table's pushing back on the paper. If you push on the table as you write, the table pushes back on you. Otherwise, your pen would go right through the table. It kind of makes sense, even though at first it's like, huh? It's pushing back on you. But it is. That's the pressure you feel between the two. If you want to prove there's equal and opposite reaction forces, if you have access to a skateboard, stand on the skateboard. And if you've got a cart in the shop, you could try this there. Don't tell John I told you. Or I say John or Jeff. Stand on a wheeled cart or a skateboard and throw a ball forwards. When you throw the ball forwards, you will find you will move backwards. The action force on the ball creates a reaction force on you from the ball, which pushes you backwards. So I'm in an office chair right now, and if I push on the desk, I move backwards. I continue to move backwards. I'm pushing the desk forward. Proof of the desk pushing me backwards is the fact that I start to move backwards. Okay, so they're equal opposite forces. You can try that ball one if you have some time and see how well it goes. The larger the force you throw the ball with, the further you should move. So if we were in a class, this would be a great one to try because I could find out who throws with the greatest force. The other thing that's going to come into play, though, is how much mass does the person on the skateboard have? Because if you're heavy, you're not going to speed up very much. If you're really light, you'll move further. So if you can find a small person to do this with that's got a good arm, even better. You've got a kid around that you know, you can test and see it throwing a ball that they can make themselves move by throwing a ball on the skateboard. Wear the helmet for safety. What if you're hammering? Well, you take your hammer, you pound a piece of a nail into the wood. The nail pushes back on the hammer. How do you know? Well, it doesn't always go in on its first hit. The nail definitely pushes back on the hammer. You get your thumb in between the two. You feel the force between the two. Okay, so you have the action force of the hammer and the reaction force from the nail. If the force from the hammer is big enough, large enough, if it's larger than it will help drive that nail in further. Okay, because you also have the wood pushing back on the nail as well. So there's a bunch of forces that come into play there. But that equal opposite reaction force is kind of one of those little weird ones. So I want you to think and apply. Told you there's going to be no math, but I'd give you these think and apply questions. So what action-reaction pairs are there between the hoist and the car? So gravity is a force. And gravity pulls this car downwards with a force. It results in a force on the hoist. But in order for the car to stay in the air, the hoist must be putting a force on the car. If the hoist wasn't putting a force upwards on the car, it wouldn't matter if we had heavy materials. It wouldn't matter what it was made out of. But because that hoist pushes on the car just as much as the car pushes on the hoist, you have to make sure you have good, sturdy materials for safety purposes. So that's one of your action-reaction pairs. And we will look at how much force does a car put on a hoist? And then we'll look at, okay, how much force is there on a piston? If there's a piston somewhere that's allowing us to control the force with which we lift that car up or lift that car down. So that takes us into a little bit of hydraulics like you would have done with braking with Jeff. So we'll bring a little tiny bit of that in as a force application, but I don't think we're going to look at that until after spring break. So this will give you a little bit of math to do, a little bit of thinking to do, and then spring break will come back and we'll do some more force calculations. And that finishes this off.